So let's go ahead and do this. So all I'm going to show you here, this is basically just the colors of the rainbow, helping you write up your Postlab. So I guess one other thing we should talk about, didn't have this ready, is again going back to the acceptable lab notebook reports. So let's talk about what we have written up and what we still need to. We did the beginning question, background information, conduct the investigation, how will I stay safe. I think we talked about all that stuff in class. So you should have your procedure written at this point. Observations and measurements, not really a lot there. Other than, I don't know, I mean, you could maybe give me just a little paragraph there on what you observed as you made the different solutions, something like that. Okay. So the observation measurement section, just give me a few sentences, and that doesn't need to be much at all. Okay, just if you give me a few sentences, that way we have the section just to have the section. But what can I claim? That's where you're going to really kind of get into what was actually happening with these reactions. Why did they make the colors that they did? And so each of you, your situations are all going to be a little bit different here as far as what you're claiming, but you need to basically explain to me how you got the colors that you got. And I'm going to help you with some of the reactions and how they occurred. So that's going to be your big, tough section, I think, on the Postlab write-up. How do my ideas and results compare with others into the literature? I don't see any way we can really meaningfully answer that question this time. So just leave that section out. Don't worry about the ideas and results or comparison section. How have my ideas changed? Now you can write something there. Okay. So the comparison section, just to reiterate, you do not need to have that for this lab. Observations and measurements, just a short little few sentences telling me what you saw when you were doing the lab. What can I claim is the big section here. And then how have my ideas changed? You can give me a few sentences on that as well. Okay? So hopefully that makes sense. That's what I'm looking for the Postlab. The reactions we need to talk about. Basically what I'm going to do now is go through all the 6 equilibria that we did and just kind of explain a little bit about their reaction and how you might have seen different things based on what you did with the reaction. Okay, now I know everyone did something a little bit different with their, to provide the stresses, so you're going to have to take what I tell you and apply it to your own situation, okay? But the first reaction is the one with bromothymol blue, the acid-base indicator equilibrium, which is on page 112 of the lab. And that one, basically, you just put bromothymol blue into water, and then you changed it back and forth with an acid base. It's just an indicator, and we don't usually think of, well, up to this point, I don't think we've thought of indicators necessarily as being equilibrium reactions, because we hadn't learned about equilibrium reactions when we first started using indicators. But that's essentially what all of them are. They're just equilibrium reactions, and by adding additional acid or adding additional base, you push the equilibrium one direction or the other, and you're going to see a color change with that shift. So that's really what's going on. I'm kind of making up, I'm not making it up, I'm just oversimplifying this because I don't think we need to get into the really deep idea of what's going on here. But basically, what we did initially is you put the bromothymol blue into water, okay? So I'm going to say bromothymol blue. Now, again, I'm cheating a little bit here. Bromothymol blue has an H on it, and the H is the only part of that molecule that I'm showing because it's a big, long, complicated molecule, and I just don't feel like writing out the whole thing. But basically, you've got an H tacked onto the end of it, and that can join up with water, and you end up with H3O+. Okay, so this is the equilibrium reaction when you put the bromothymol blue into water. Kind of looks something like this. Okay, and I think this will make even more sense when we get into the next unit and we start talking about acid-base equilibrium reactions, which is where we're going next. So the idea here is that if you add OH minus to this side right here, it's going to react with the H+, okay, to form more water, okay, which would then push the equilibrium basically this way. Oh, I guess the other thing that I should note here is that this side is yellow. Okay, so you push the equilibrium in this direction, you're going to get more of a yellow color. Push it more this direction, you're going to get more of a blue. Okay? So, if you add, well, let's start with the easy one. If you add acid, you're basically adding additional H3O+. Okay, so if you put the HCl into there, you're adding a product that's going to push the equilibrium this direction and make it more yellow. Okay? If you add hydroxide, then the hydroxide is actually going to react with the H here, okay, and make additional water, which is going to push the equilibrium this way, okay, towards the blue. So that's kind of the way that equilibrium works. Hopefully that's not overly complicated. I'm trying to keep it simple here. But basically that's your first reaction. That's your bromothymol blue reaction, okay? The next one, you've got the first of the complex ion equilibria. That's the iron chloride and potassium thiocyanate. What happens when you combine those two is FeSCN2+. Okay?
Please report to the activities office.
Now,
Lowe's to the activities office.
can't get that nonsense straight. So the important equilibrium that's happening here, you've got Fe3+. On one side of this thing, you've got Fe3+ and SCN-. Okay? That's an equilibrium with the FeSCN2+. Okay? The Fe3+ ions are kind of like an orange, yellowish color. Okay? I don't know exactly what to call it. The FeSCN2+ ions are kind of like a blood red. Okay? Really, really deep red. So, you're adding a bunch of things to that equilibrium system to push it one way or the other. So you can kind of think about, like, for example, if you put in, let's see, the stresses that they give you, 0.1 molar KNO3. So you can kind of think about, would KNO3 really change anything in this equilibrium? You can also think about whether solid FeCl3 would change anything. Now, when you put FeCl3 into that solution, you need to understand, as soon as you dump that in, this is going to dissociate, right, into Fe3+ and 3Cl-, okay? And then you can kind of think about, well, would that affect the equilibrium in any way? And it should, right, because essentially what we're doing is adding a reactant. So then you can think about which direction that would push the equilibrium. Should push it towards the product side, so you should see, if you're adding FeCl3, a little bit more blood red, okay? Same thing if you're adding the solid KSCN, because, again, you're adding some FCN-, that would push it more towards blood red. I'm not going to tell you why you saw it shifting back the other direction with the phosphate. I want you to see if you can figure that out. Here's the hint that I will give you. Iron phosphate is insoluble in water. In other words, it will form a precipitate. Okay? You can maybe think about that one and try and figure out why it is. Because I think most of you probably observed when you put the phosphates in, it changed back to that orange-yellow color, and then eventually, if you added too much, the color would go away completely. Okay? So you can kind of think about why that might be the case. Your next equilibrium system was the copper 2 sulfate and ammonia. Okay, this one's kind of cool. So you've got copper sulfate, and this one I'm probably going to have to explain in a little more detail. So basically you've got the copper 2+ ion, okay? And this one's a little tricky. So copper 2+, and you've got... yeah, I don't know if I can explain this in one equilibrium necessarily. Okay, so here's maybe your equilibrium that you've got going on this one. Can I do this? Does it say what complex ion forms? I'm guessing it's CuNH3,4. Not positive about that. Plus, what else do we have here? 2OH minus. Is that balanced? Well, I think there's got to be 4 of these. Okay. I may be cheating a little bit with that equilibrium, but we're gonna go with that. So basically what's happening here, when you first add the NH3, and this is the part that you guys might struggle with a little bit because we haven't really talked in a ton of detail about the way that certain bases react in water. It's been since the very beginning of the year we kind of did talk about this. But if you've got something like NH3, it's a base because it can take a hydrogen from water. Okay, so you've got another equilibrium going on here to form NH4 plus OH minus. So what you've got going on here basically is that NH3 is helping to form OH minus at the beginning of this thing. Okay, so you've got this thing in some sort of equilibrium. Okay, when you first add, there's this OH minus being created here. Okay, so it's essentially like you're adding a product, which pushes it back towards the copper hydroxide. And that's that blue solid, that blue precipitate that you saw forming in the bottom of your test tube. Okay, but because you're adding NH3, that's also a reactant over here. Okay, so this gets a little tricky. When you add enough of the NH3, now it kind of overwhelms the fact that you're making OH minus because you're just adding all this NH3, and now the copper suddenly says, oh, I'd rather form the complex with the NH3 because there's so much of it in here. So then what happens is this reaction becomes predominant, and it starts going towards the products, and then you end up with CuNH3,4, which I think gave you a really deep blue, almost purple type color. Okay? So again, that one's a little complicated because there's a couple of things going on there with the same reactant. It's interesting that you can add a little bit of NH3. It produces this OH minus because the NH3 is reacting with the water. And then because you produced OH minus, that's going to react with the copper to make the copper hydroxide. But if you add enough of the NH3, if you, and this is the way they always phrase this in these coordination complex problems, is that you just you flood it with the NH3 or you add an excess amount of NH3. Then instead of reacting so much with the water, the NH3 is going to start reacting with the copper instead, and it's going to form the, so you've got the light blue solid over here. And then you got the coordination complex, which is kind of like a deep blue over on this side. Okay? So there's your equilibrium for that. I know that one's complicated. The fourth one, are we on the fourth one? I think so. Equilibrium system can be formed in a solution with copper 2 chloride in water. The copper ion bonds to 6 water molecules on this one to form the hydrated complex ion CuH2O6, 2+, while the Cl- ion remains in solution. Okay? To create the equilibrium mixture, add about 2 grams of copper 2 chloride to 25 milliliters of water. And then investigate the shifts that can be observed here. Okay, this one is very similar, actually. If you look at the cobalt reaction down below on number 5, you see how the cobalt is complexing with the H2O, and then you've got the chloride ions in there. And then on the other side, you've got the cobalt complexing with the chloride. Well, the copper will do the same thing, okay? So what you should have on that one, again, very similar to this other reaction, you should have the copper CuH2O6, which is a 2+, okay? Plus the, I'm going to guess this is a 4 also because the copper is a 2+. I could be wrong about that. Probably should have done my research on that one. So then that's going to end up giving you the CuCl4 complex, which would be a 2- charge, just like in the cobalt reaction, plus 6H2O. Okay, so very, very similar to the cobalt one. And this over here, the copper, when it's complexing with the water, is going to be a bluer color. When it complexes with the chlorine over here, chloride, it's going to end up being more of a green color. Okay. So what you should have seen, now I don't know how many of you had a chance to do this one, or I feel like this one wasn't working out as well for some reason, but what you should have seen on this one is if you're adding the concentrated HCl, that's kind of going to do the same thing, right? You're adding this Cl, so now the copper leaves the H2O complex that it was in, and it becomes part of the CuCl4 complex. So adding the HCl should have pushed the equilibrium more towards the green. And then if you dilute it again, that should have pushed it back towards the blue, because now you're adding more water. So it's just basically whichever of these complexes is winning out, okay? The fifth equilibrium I don't think I need to talk about, because that was, not only did they give you the equilibrium reaction right here, and it is very much like the one we just talked about, but that one was also in the pre-lab, so I don't know that we need to talk about that one a whole lot. And then the last one didn't really work out for anybody, but in theory, you've got the equilibrium reaction here, and this is fairly complicated, okay? But the methyl red is red, it says in the original soda water, but once the CO2 is moved into the gas phase, it becomes yellow, indicating the shift to the left, okay? So actually, this one kind of even tells you how it's working. Now the reason the CO2 moves into the gas phase is because you've reduced the pressure over it, and if you reduce the pressure over it, the CO2 will leave at that point. Okay, and so then when the CO2 is leaving the solution, it's becoming less acidic, which is going to cause the methyl red, which is just an indicator. It's going to cause it to change color. Okay, so that one, I don't think anyone ultimately did that one to make your rainbow, but just in case you did, the last one is pretty much given to you in the explanation on the soda water and methyl red. Okay, I know this stuff is complicated, and I know that looking at it is probably like, what is going on here on some of these, but just know that this is going to make a lot more sense once we dive into the acid-base equilibrium chemistry, and also even once we get to a little bit of the solubility equilibrium stuff that we're going to talk about after that. Okay, so as long as you have an idea of why these things are working, and you can figure out, oh, okay, so we added a reactant here that's going to push it towards the product. We added a product that's going to push it towards the reactants. And hopefully you guys did something with the temperature on the cobalt reaction. Notice that in the cobalt reaction, they put heat on the reactant side, which means it's an endothermic reaction. So that should help you to figure out why changing the temperature the way that you did caused the color changes that it did. Okay? So I think that's pretty much it as far as the write-up. Hopefully that makes sense. And then you guys will just use your individual situations to explain why you got the colors that you got and how you created those colors. All right. See you guys in class tomorrow.